Let's take up group 15. All the elements form two types of oxides, E2O3, E2O5, that is trioxide and pentoxide. In oxides, in higher oxidation state of element is more acidic than in lower oxidation state, and acidic character decreases down the group because metallic character increases and non-metallic character decreases. The oxide of the type E2O3 of nitrogen and phosphorus are purely acidic. That of arsenic and antimony are amphoteric, means acidic as well as basic, and bismuth is predominantly basic because it has metallic properties. Oxidation state: in +1, nitrogen forms nitrous oxide; in +2, it forms nitric oxide; in +3, nitrogen forms dinitrogen trioxide; phosphorus forms phosphorus trioxide, which exists as dimer, and all other trioxides of arsenic and antimony also exist as dimer. Bismuth trioxide exists as monomer. Nitrogen forms N2O4 dinitrogen tetraoxide, which is dimer of NO2. Another oxide NO2 is formed, nitrogen dioxide. So nitrogen dioxide on dimerization gives N2O4. N2O4 is colorless and NO2 is brown in nature. Pentaoxide: nitrogen forms dinitrogen pentaoxide. Phosphorus forms dimer of P2O5. Arsenic also forms dimer of As2O5. This is Sb4O10 is dimer of Sb2O5. Oxides of nitrogen we'll take up in detail. First one, we have nitrous oxide. Oxidation state is +1. How to prepare? It is prepared by heating ammonium nitrate, which gives N2O plus 2H2O. It is colorless gas and neutral in nature. N2O nitrous oxide is also called laughing gas because it attacks nervous system, and it is used as anesthetic in minor dental surgery. Nitrogen monoxide NO plus 2 oxidation state is prepared by reaction of NaNO2 FeSO4 in presence of sulfuric acid, which changes to ferric sulfate plus 2 NaHSO4 is formed plus water and NO is formed. It is colorless neutral oxide. NO is also formed by lightning. In lightning or during lightning, nitrogen reacts with oxygen to form nitrogen monoxide. And nitrogen monoxide is paramagnetic in nature due to presence of unpaired electrons. Dinitrogen trioxide N2O3 oxidation state is +3. NO plus N2O4 react together to form 2N2O3. It's a blue colored solid, acidic in nature. Nitrogen dioxide NO2 oxidation state is +4. It is obtained by heating lead nitrate, which gives nitrogen dioxide, which is brown in color, plus 2 PbO plus O2 is formed. It is brown gas and acidic in nature. NO2 forms dimer N2O4. Oxidation state is +4. NO2 on cooling, 2 moles of NO2 on cooling gives N2O4, and if heating is done, it changes to NO2 again. It is colorless solid, liquid and acidic in nature. NO2 is also paramagnetic in nature due to presence of odd electron, due to which it forms dimer. N2O4 is diamagnetic because it does not have unpaired electrons. N2O5 plus 5 oxidation state, it is prepared by reaction of nitric acid with P4O10, which acts as dehydrating agent. It removes water from nitric acid and gives N2O5 plus metaphosphoric acid, HPO3 is formed. So N2O5 is anhydride of nitric acid. It is colorless, solid and acidic in nature. Structure of oxides of nitrogen. NO2 has got one coordinate bond and one double bond. In resonating structure, this will become double bond and this will be coordinate bond. And there is this odd electron makes it paramagnetic in nature. Bond angle is 134. And bond length is equal due to resonance 120 picometer. Hybridization is sp2. In N2O4 we have this double bond, here double bond, this is coordinate bond, this is coordinate bond. In resonating structure, this will become coordinate bond, this will be coordinate bond, this is double bond, this is double bond. Bond lengths become equal due to resonance. Bond angle is 135. Bond length here is 175 picometer. Remaining all bonds, NO bonds, are 121 picometer. Each nitrogen is sp2 hybridized, so it is planar shape. In N2O5, here we have double bond, here we have coordinate bond. These two are single bonds. Here double bond, this one is coordinate bond. In resonating structure, this becomes coordinate bond, this becomes double bond, this single bond is as it is. Here we get double bond and here we have coordinate bond. So all these four bonds are equal. Their bond length is 119 picometer. This bond length is 151 picometer. Bond angle is 112. This is also planar because each nitrogen is sp2 hybridized. NO is neutral and is not an acid anhydride. 2NO reacts with oxygen to form NO2, which is mixed anhydride of nitrous and nitric acid. NO reacts with Cl2 to form nitrosyl chloride. N2O3 is anhydride of nitrous acid. N2O5 is anhydride of nitric acid. And NO2 is mixed anhydride of nitrous and nitric acid. N2O and NO are neutral. NO readily forms coordination complexes with transition metals. For example, ferrous ion combines with NO to form a complex. This complex is formed in the Brown ring test for nitrate. Reactivity towards halogens. These elements react to form two series of halides, trihalides and pentahalides. All the trihalides of these elements except those of nitrogen are quite stable. Trihalides except BiF3 are predominantly covalent in nature. BiF3 is ionic in nature. Except NF3, the halides of nitrogen, NCl3, NBr3 and Ni3 are unstable and highly explosive compounds. So the halides of other elements of this group are fairly stable. The anomaly is due to high electronegativity of nitrogen. The trihalides have tetrahedral structure or geometry involving sp3 hybridization of the central atom, but the shape is pyramidal due to presence of lone pair of electron on the central atom. And due to the presence of lone pair of electron, they act as Lewis bases. In case of nitrogen halides, tendency to act as Lewis base decreases from Ni3 to NF3. Ni3 is the strongest Lewis base and NF3 is weakest Lewis base because fluorine is most electronegative, iodine is least electronegative. Also, the tendency to act as Lewis base decreases from nitrogen to bismuth for a given halide because electronegativity decreases. The trihalides of phosphorus and antimony, especially fluorides and chlorides, act as Lewis acids and accept negatively charged ions by using vacant d orbitals. This is not possible for nitrogen because nitrogen does not have vacant d orbitals. Except NF3 and PF3, all the trihalides are hydrolyzed by water and the product of hydrolyzed are different. NCl3 on hydrolysis gives ammonia and hypochlorous acid. NF3 cannot be hydrolyzed because HF is not stable. PF3 also cannot be hydrolyzed because HF cannot be formed here. PCl3 can be hydrolyzed to get phosphorus acid, H3PO3 and HCl. Arsenic chloride reacts in the same manner to form arsenous acid and hydrogen chloride. Antimony and bismuth hydrolyze to form their oxychlorides. SbCl3 on hydrolysis gives SbOCl, antimony oxychloride plus 2HCl. Similarly, bismuth chloride get hydrolyzed to bismuth oxychloride plus 2HCl due to their increased metallic character. Reactivity towards metal. All these elements react with metals to form their binary compounds exhibiting -3 oxidation state. For example, calcium nitride, calcium phosphide, sodium arsenide, zinc antimonide, and magnesium bismuthide. Sulfides. With the exception of nitrogen, all the elements of this group form sulfides. The sulfides of arsenic and antimony are soluble in yellow ammonium sulfide or simply ammonium sulfide and form thio compounds. Arsenic sulfide reacts with ammonium sulfide to form ammonium thioarsenide, which is soluble in water. Arsenic pentaphosphide reacts with ammonium sulfide to form ammonium thioarsenate. Antimony sulfide gets dissolved in ammonium sulfide to form ammonium thioantimonide. Antimony pentasulfide dissolves in ammonium sulfide forming ammonium thioantimonate. Sulfides are also soluble in caustic alkali, that is NaOH. Arsenic sulfide will dissolve in NaOH forming sodium thioarsenide and sodium arsenide plus 3 water will be formed. Stability of sulfide increases with the increase in atomic number of the element due to increase in metallic character.